Surface area of solids with internal depressions, Introduction. Welcome, everyone. Today we are diving into a very interesting topic in geometry, the surface area of solids with internal depressions. Now, let's start with the basics. In our study of geometry, we often encounter shapes that aren't perfectly solid all the way through. Imagine an object that has parts carved out or hollowed out from its center or its surface. In mathematical terms, we refer to these hollowed-out sections as an internal depression. As we begin this lesson, I want to address a very common point of confusion that I see many students struggle with. When you see a hole being carved into a shape, your first instinct might be to think, since material is being removed, I should subtract the area of that hole from the total. It feels logical, right? But be very careful here. The key to mastering this topic is to remember exactly what surface area means. Surface area refers to the total area of all surfaces that are exposed to the outside, essentially, any part of the object that you could touch. Think about it this way. When you carve a hole into a solid, you aren't actually removing surface area. Instead, by removing that material, you are actually creating brand new surfaces that were previously hidden deep inside the object. Because these new surfaces are now exposed, we don't subtract them. Instead, the surface area of the internal depression must be added to the exterior surface area of the remaining solid. Keep this principle in mind, because as we move to the next slide, we will look at the conceptual logic that proves why this addition is necessary. Surface area of solids with internal depressions, the conceptual logic. Now that we've introduced the concept of internal depressions, let's dive into the conceptual logic to really make this click. To understand why we add area instead of subtracting it, I want you to imagine a solid wooden block sitting in front of you. Suppose you take a drill and create a hemispherical hole right into the top of that block. Now, look closely at what happened to the surface. You're right that the original flat top surface of the block has been reduced because some wood was removed. However, by drilling that hole, you have simultaneously created a new bowl-shaped cavity inside the block. Think about it this way. If you were to run your finger inside that new hole, you could actually touch the inside of that bowl. In geometry, the rule is simple. If you can touch it, it is an exposed surface. And because it is an exposed surface, its area must be included when we calculate the total surface area, or TSA. This leads us to our general rule, which you should memorize. The total surface area is equal to the exterior surface area of the remaining solid, plus the interior surface area of the depression. As we move into the next slide, we will break down a specific methodology you can use to apply this rule to any complex shape you encounter. Surface area of solids with internal depressions, step-by-step methodology for calculation. Now that we understand the core concept, that carving out a hole actually adds new surfaces rather than removing them, you might be wondering, okay, teacher, how do I actually approach a problem like this on an exam? Well, I have a reliable 5-step methodology that you can follow every single time to ensure you don't miss any surfaces. First, your very first step is to identify the base solid. Before you look at the holes or the carvings, look at the original, untouched object. Ask yourself, is this a cylinder, a cube, or perhaps a cone? You need to know the foundation you are working with. Second, you must identify the depression shape. Look closely at the part that has been carved out. Is it a hemispherical bowl? Is it a smaller cone being removed from the top? Identifying this shape is crucial because it tells you which new surfaces have been created. Third, and this is where most students succeed or fail, you need to list all the exposed surfaces. I want you to imagine you are holding the object and running your fingers over it. Every single surface that is touchable, whether it is the outer exterior wall or the inner surface of the hole, must be noted down. Fourth, once you have your list, it is time to apply the formulas. For each part you identified, find the appropriate mathematical formula. You will likely be using curved surface area, or CSA, for the walls and the bowl, or perhaps total surface area, or TSA, if a flat base is still present. Finally, the fifth step is simply to sum the areas. Take all those individual areas you calculated and add them together. This sum will give you your final total surface area. To show you exactly how this works in practice, let's move on to our next slide, where we will apply this exact step-by-step method to a real-world example, a bird bath. Surface area of solids with internal depressions, real-world example, the bird bath. Imagine a bird bath designed as a solid cylinder with a height of h and a radius of r to make it functional. A hemispherical depression, also with the same radius r, has been carved out from the top to hold water. Our goal here is to find the total surface and area, or TSA, of this entire bird bath. In step 1, we need to identify all the exposed surfaces. If you were to run your hand over this bird bath, what could you touch? First, you would touch the exterior curved wall of the cylinder. Second, you would touch the interior curved surface of the hemispherical bowl where the water sits. For this specific model, we are focusing our calculation on these two curved surfaces. Moving to step 2, we need to write down the mathematical formulas for these individual components. For the curved surface area, or CSA, of the cylinder, the formula is 2 pi rh for the curved surface area of the hemisphere. The formula is 2 pi r squared. Now, in step 3, we combine these areas. Recalling the rule from our previous slides, that we add the area of the depression to the exterior area, we see that since both the outer wall and the inner bowl are exposed, we must add them together. So, the total surface area of the bird bath equals the curved surface area of the cylinder plus the curved surface area of the hemisphere. Finally, in step 4, we simplify our mathematical expression. We start with the equation, total surface area equals 2 pi rh plus 2 pi r squared. To make this formula cleaner, we can take the common factor, which is 2 pi r, out of the expression. This leaves us with a much simpler final formula. Total surface area equals 2 pi r multiplied by the quantity h plus r. Now that we understand the conceptual logic of adding surface areas, let's put this into practice with a concrete example. Let's look at slide 4, where we will analyze a real-world object, a bird bath. To solve this, we will follow a systematic 4-step methodology. As we move to the next slide, keep this calculation in mind, as we will discuss some common pitfalls where students often make mistakes during this exact process. Surface area of solids with internal depressions, common mistakes to avoid. First, let's talk about what I call the subtraction trap. This is the most frequent error I see. Many students think, since material was removed from the solid to create the whole, the area must also be removed. This is a logical error. You must remember this golden rule: subtract for volume, but add for surface area. While the amount of matter decreases, the amount of exposed surface increases. Next, be careful not to ignore the base of your solid. Always ask yourself, is the bottom surface exposed? Let's look back at our bird bath example. If the bird bath is sitting permanently on the ground, you might not need to include the bottom area. However, if the problem states the object is being painted on all sides, you must remember to add the area of the circular base, which is pi r squared. Finally, watch out for confusing curved surface area and total surface area. When a depression is made, you will almost always use the curved surface area of the carved-out shape. Why? Because the flat lid, or the top circular face of that shape, has been removed to create the opening of the hole. It no longer exists as a surface. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of adding surfaces, it is very easy to fall into certain traps during an exam. Keep these 3 points in mind, and you will avoid the most common mistakes in these types of problems. Surface area of solids with internal depressions, key takeaways. First and foremost, remember the golden rule we discussed at the very beginning. An internal depression actually increases the total surface area of an object. Even though you are removing material, you are creating new, reachable surfaces that didn't exist before. Secondly, when you are performing your calculations, always treat the surface area of the interior of that depression as an additional exposed surface. If you can touch it, you must add it to your total. Finally, let's look at the specific formula we derived in our birdbath example. For a cylinder that has a hemispherical depression with the same radius, the combined area of the curved surfaces is expressed as total surface area equals 2 pi r times the quantity h plus r. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing our key takeaways to ensure you have a solid grasp of this concept. Keep this formula in your toolkit and always remember, subtract for volume, but add for surface area. Great job today.